Welcome back to this series of videos where I'm looking at an old DOS game called Paratrooper, and I'm trying to figure out how the code works by reverse engineering it. So if you haven't seen the previous video, you should probably watch it first. Because we are going to start immediately with Cutter, loading the file from last time, so the para.com file. And notice here that I'm recreating the project. I did not save the previous project because Cutter still has a few issues, and one of these is that when you save a project, it will not save the offset at which you loaded the program. And so in my case, I need the program to be at offset 100. Since it's not saved, if I would save the project anyway and then reload it, then everything would be offset and nothing would make sense anymore. So I'm just recreating it every time, which is not a big deal because it's pretty fast to recreate. So now I'm going to go to the address 2C40, which is the entry point that we found last time, then type AF to analyze the function, and then refresh the contents. So this should look familiar. That's the entry point of the program that we looked at last time. So it's initializing the video mode. And we reach the end of this block here. So what we will look at this time is what immediately follows. So there are two ways of entering this block. One is by exiting the initialization, and the other one is through this arrow, which is coming from further down, which is coming from here. And so this is indeed a loop. So if I unzoom a little bit to put the whole loop on the screen, we have this. It's not a big loop, but there are still a few interesting things happening in there, and that's what we're going to look at now. Starting from the beginning, and the beginning is these two blocks. We can see that they have a lot of similarities. They both put 0 in AH, and then they call an interrupt, 1A. Immediately after calling this interrupt, they do something with dx. Okay, so calling interrupt 1a, subfunction 0, and then looking at the dx results. Let's have a look at the documentation. So 1a0, read the system clock counter. And we've seen that we are using the result dx, which says low order word of the tick count. So the system clock is something that increments approximately 18 times per second. And so 18 times per second, the value of dx will change. So what are we doing with this dx value? Well, first, before that small loop here, we read the tick count and we store it inside bx. We can see that we are not going to modify bx, but we do an XOR between bx and the new value that we got by calling that interrupt 1a again. Since we do an XOR, the result we get is something that has all the bits that changed set to 1 and all the bits which remained the same set to 0. Then we test that XOR result and we test it against FC. And so a test is an AND. So we do an AND between this and 0xfc, which in binary is 6 ones followed by 2 zeros. And then if the result of that test is 0, then we loop over that small block here. In other words, we are going to exit that block only when a bit beyond the first two changed, because the first two bits here are set to 0 in the mask. So if any other bit changes, we exit the loop. So what this whole thing is doing is read the timer, store that value, then repeatedly read the timer and check if any bits beyond the first two are different. So imagine that the value in the timer was something like this initially. Then one tick later it's going to be this. Then one tick later, it's going to be that. One tick later, it's going to be this. And then finally, it will be that. And so at that point, well, all these bits have changed. But before that, there was no change beyond the first 2 bits. Once I will do an XOR between this and the initial value, what I will get is this. And I will do an AND. So this is my test with 0xfc, and that will give me this, which is different from 0, and then I will exit the loop. But what if the initial value was not this one, but it could have been this one, or maybe this one? Well, this means that the amount of ticks that I will wait can be 1, 2, 3, or 4 ticks. So that doesn't look that great, because the delay is going to depend on when I started the program. But keep in mind that we are inside a loop here, and that what follows that little wait routine that we're currently looking at, well, what follows is pretty simple. So there's a pretty good chance that we will get back to that waiting routine in so little time that the timer will not change in between. Which means that once we triggered the break from the loop, the last 2 bits are 0, and they will still be 0 when I will come back into that loop. The first time that we are waiting, well, indeed, we might wait 1, 2, 3, or 4 ticks, but all the subsequent times, we are always going to wait 4 ticks. And how long is 4 ticks? Well, since a tick is roughly 1/18th of a second, I can say that 4 ticks is going to be roughly 1/5 of a second. So this is a delay that ensures that this big loop is running approximately 5 times per second. All right? How can we figure out what it's waiting for exactly? How can we figure out what this loop is doing by just looking at the timer? Well, maybe not so much by looking at it, but by changing it. We certainly can see what the impact on the game is. What determines how long we are going to wait is this value fc, the mask. So if I would turn this mask into something that would make it wait much longer, and let's say, for example, that I would set the 4 rightmost bits to 0 instead of having the 2 rightmost bits set to 0. How long should this wait? Well, instead of waiting for 4 ticks, it should wait for 16 ticks. And since the timer is running at roughly 18 ticks a second, well, 16 is close enough to 18. I should have a loop that runs once a second, approximately. Let's try that out. I still have that little program that I wrote last time. You might remember the 2 values here that we set to mess around with the palette. The only thing that I've added are 2 small convenience functions here to read and write words into the program, simply because I cannot directly do pointer casting with C#, but that's a detail. I could make the program and save whatever, but yeah, let's not worry about this. The only thing that matters is that I now have a function that allows me to write and read words. So which value should I change in the code exactly? So this test instruction is at address 2ccd. And if I look at the next instruction, I can see that it's 2cd1, which means that the previous instruction, starting at D, has a length of D, E, F, and then 0. So it's a length of 4 bytes. All right, let's do px4 to see what my instruction looks like. F7, C2, FC00. So I can see that my constant value FC is here. This is the 3rd byte of the instruction, and that's the one that I want to modify. Let's log this value. So Vx of the current instruction location plus 2, because that's the second byte I want in there, minus the offset of 100, which is where I loaded the program. And so I have 2BCF. Let's copy this into the program here, and I will say ROM at 2BCF equals 0F0 instead of FC. Save this, run it, and now we can look at DOSBox again. So one thing I've added since last time is that I'm running DOSBox with DOSBox dot, which mounts the current folder as the C drive, -C mixer master 00. And mixer master 00 simply sets the sound volume to 0. Because honestly, after hearing that little intro tune hundreds of times, I got tired of it. So I'm running DOSBox muted. So para2, and let's see what increasing the delay changed to the game. So now it's waiting 1 second per loop instead of 1/5 of a second. And it should be pretty obvious that the title is now displayed much slower than before. We are getting roughly 1 character per second. Well, that should be enough to conclude that we are looking at the loop that displays the title of the game. Let's see how it does that. But just before, maybe we can figure out how many times this loop is going to loop. If I look at the branch instruction at the bottom of the loop, I can see this: decrease BP, then jump not equal, or jump not 0. So we are decrementing the BP register, and as long as it didn't reach 0, we just go back to the beginning of the loop. Decrementing BP twice. This is important. Well, what is BP set to? We have to look at the beginning of the loop, or right before the loop, and we'll see this: mov BP 16 in hexadecimal, which is 22 in decimal. Okay, 22 divided by 2, because we are decrementing by 2 every time, so 22 divided by 2 is 11. And if we count the letters in the title of the game, Paratrooper, P-A-R-A-T-R-O-O-P-E-R, well, it's 11 characters. Well, another confirmation that we are looking at the loop displaying the characters. We loop 11 times, we have 11 characters. So every pass in the loop displays 1 character. Let's see how it does that. After waiting for a little bit, we get to this thing. So we are calling another interrupt, and we are calling it twice. But once with AH set to 1, and one with AH set to 0. All right, what is this? Interrupt 16, 0 and 1. And so we start with 1, which is get keystroke status. And then we go to 0, which is wait for keystroke and read. So looking at get keystroke status, we can see that this is something that checks if a key is pressed, but it's not going to wait, it's not going to block in there. And if a key is pressed, the Z flag will be set to 0. So if a key is pressed, ZF is 0, so it will take the red arrow here and gets here. But if a no key is pressed, then it will follow the green arrow and end up here. So we enter this block here only if a key or something has been pressed. And this part here reads the key, and it will put that key into AL as an ASCII character. Then it compares, at least the code here compares AL with 13 in hexadecimal, which is 19. And based on the result of this, it will either continue here or enter that single instruction block here that negates a byte in memory. This says jump not equal. So if AL is not 19, then we just keep going. But if AL is 19, then we will do a 1's complement to the byte at address 216B. Well, what could be there? Let's have a look. So this addressing mode will always take the DS value as the segment. We can do 216B plus 0x110 because that's the value of our DS segment. And so we have 227B, and I will go to 227B, and I will print, let's say, 20 bytes. And so what we have there is a small block of memory which contains the value 01, 00, 01, 00, and so on. It repeats, right? What if I would just look a bit before that in memory? Let's say at 5B instead of 7B, and now I will print 40 bytes. Well, I can see that before that address, the memory contains stuff that looks a bit more interesting, or at least less repetitive. And starting from address 227B, it becomes that sequence or that repetition of 0100, 0100. So that would flip the value here and turn it into FF. Well, okay, that's interesting, but that tells us very little about the purpose of this thing so far. We'll just keep note of that, and we'll have a look at it if we encounter this address again. But maybe we can check what this character is, 19. And this is quite interesting because I type ASCII table. Let's look at this one. All right. 13 in hexadecimal is going to be this thing here, which says device control 3x off. And this is actually a special character, which is a non-printable character, which is used for serial communication. And so you have X on and X off, which are control signals. So that is a bit mysterious to me. I don't really know why the game does that. But what I know is that I'm not expecting to receive anything through the serial ports. This might be safe to skip at this point. As I said, I'm not quite sure what's going on there. It might be related to the joystick. We'll eventually figure that out later. But so we get to this point here. And this is where we would get if there was nothing in the buffer. And there we have CLD, which is something we've seen last time. CLD sets the D flag, and the D flag is the decrement flag that controls the string operations. And we've seen the LOD S string operation last time. Well, this time we see that we have a MOV S string operation. So string operations access memory from a segment and an index, and they will increment or decrement that index every time. And this is controlled by CLD. So CLD being cleared, it means that the index will be incremented every time. And so here we have a MOV, SW, SW, and one SB, which corresponds to word, word, and byte. And these instructions are using DI and SI, and with the D flag set to 0, DI and SI will be incremented every time. They will be incremented 2 times when dealing with words, and only 1 time when dealing with bytes. What we have here, these 3 MOV instructions, are operating on 5 consecutive bytes, which is something to keep in mind. 5 bytes. Then that little block of code that moves 5 bytes is inside a loop. What happens in that loop? Well, immediately after moving these 5 bytes, we are incrementing DI. And so DI is the index of the destination. Then we do a few things to the offset, which increments DI. We'll get back to this in a moment. And then we loop. So we repeat this a certain amount of times. Let's look at one of these MOV SW instructions. So they read from the right side and they write to the left side. So where are they writing? They write to ESDI. So ES is the segment, and where is it coming from? Where is it set? Well, if I move up a bit, I will get back to this line here, where we set ES to B800. And so B800, well, if you're familiar with CGA graphics, this might sound familiar to you, because B800 is the address of the frame buffer of the graphics card. This is where the values of the pixels are stored. Remember that it's B800 for the segment, but so we multiply it by 16 to get the linear address. We have something here that writes into video memory at a certain index, which is given by DI. And so where is DI initialized? Well, it's initialized before the loop that displays the characters. And it's initialized to this value, which should correspond to the corner of the title. So probably the upper left corner, we'll see. But so it's not inside the loop, because of course the loop displays characters one by one and each character has to be at a different location. So this is going to be the location of the first character. So we'll see how DI is changed through this loop, and it's changed here. Then we have something that reads memory, and so it's reading it from SI. So it's an index, and by default the segment is given by DS, so the data segment, which is set to the segment that currently contains our program. So we are here reading something from the memory of our program. SI is itself initialized to a value which is also read from memory. And it's also read from something that depends on DS. And an index, which is an offset plus a BP. And BP, well, remember, this is the loop counter. So we decrement it here twice. And we can see here the reason why we decrement it twice, because it is an address from which we are going to read an index. And an index is 2 bytes. So every time we go through the loop, BP has to change by 2 bytes to make sure that we are reading the next, or in this case, the previous address, because BP is decremented twice. Obviously, this is dealing with displaying the characters, but how does it do that exactly? Well, we are looking at 5 bytes, 5 consecutive bytes. Then these 5 bytes are repeated a certain amount of times. How many times exactly? Well, we have loop here, and the loop instruction depends on the value of CX. And CX is set to 18 in hexadecimal, which is 24 in decimal. So we are moving 5 bytes 24 times. And now might be the good time to start looking at what the game actually puts to the screen. And to do that, I took a screenshot of the game's title screen, which is here. And I will zoom on this quite a bit to look at the characters that we have here. Because I've seen that we are working in chunks of 5 bytes. And in CGA graphics mode, we only have 4 colors, which means that every pixel is 2 bits. 2 bits means that each byte can be 4 pixels. We have 5 bytes, 4 pixels per byte, which means 20 pixels. We are moving 20 pixels every time we enter that little loop here. Well, let's see what 20 pixels look like on this picture. And I can also, where is this thing? Yeah, I can show the grid in this tool, which is going to be convenient. And here I'm going to draw bytes. So a byte is 4 pixels. So let's say that I have 4 pixels here, 4 pixels here, 4 pixels here, that's 3 bytes, 4 pixels, and then 4 pixels. That's 5 bytes. And so these 5 bytes, these 20 pixels, well, that looks like it's the width of one of the characters. I don't know yet if the characters start really on their upper left corner or if they start 2 pixels to the left, because as you can see, that width of 20 pixels could be one or the other, or they could even be centered. But at least it makes sense. It's really the width of a character, and it does not overlap with the next one. Well, vertically, how many pixels do we have? Well, I will do the same thing, and I will mark blocks of 4 pixels. That makes it easier to count, even though in this case bytes do not really make sense, but I'm just counting the pixels. And so 4 more here. Right, so this is the height of my letter, and so I have 1, 2, 3, 4, 5, 6 blocks of 4, which means 24 pixels. This is the height of my characters. 24, well, this matches what I have here. So it's 24 lines of 20 pixels each. So this all makes sense. I am reading the address of the letter that I want to display, and I put that into SI. Then I'm reading all the pixels from that character and I'm putting them to the screen. But so there is something that might look a little bit odd here, which is that after writing 20 pixels, well, I should go to the next line. And so going to the next line should be adding something to DI. Well, what am I adding to DI? I'm adding BX. And so what I would expect BX to be is just the width of a complete line on the screen minus the 5 bytes that I used here. So I would end my line here, and then I would skip all the pixels to the right to come all the way around and start rasterizing the second line here. Well, but if I look at the value of BX, I'll notice that it's oddly large. Well, that value 1 FFB is really close to 2000 in hexadecimal. Actually, 1 FFB is just 5 less than 2000. And these 5 less is something that I would expect, because it should be something that puts us at the beginning of the character on the next line. So being 5 less than some sort of number that describes the line makes sense. But this is really big. This is 2000 in hexadecimal. And so 2000 in hexadecimal is going to be 8K, 8 kilobytes. Well, this is where you need to know one more thing about the CGA graphics card, which is that it uses 2 pages. And so these 2 pages are mentioned here when you look at the graphics mode. And it says that all the memory is used for the frame buffer. Each row is 18 bytes. So yeah, the horizontal resolution is 320. If you divide that by 4, because 4 pixels per byte, you get 80. So 80 bytes. Well, then I would expect 80 bytes minus 5, so 75 bytes to go to the next line. Except that the first set of rows, which are the even rows, 0, 2, 4, and so on, they are at the beginning of the memory. And the second set with the odd rows is 8 keys further. They are on the second page. Blitting stuff into the CGA graphics memory is a little annoying because of this, because you cannot simply go from one line to the next. You need to always jump back and forth between these two pages. So the reason why this is done this way is, well, probably to deal with interlaced pictures, as they say here, but indeed, it's a pain to program. Looking back at the code, we can see that here we are adding 8k minus 5 bytes. We go back to the beginning of the character, but on the second page, and in a way we are still on the same row, but because it's the second page, then it's one row more. But then the next time we will have to go back to the first page to rasterize the third row. How is this going to happen? Well, we can see that we do ones complement to bx. Bx here was plus 8k minus 5. By doing neg bx, it becomes minus 8k plus 5. If I would just add this, so if I did not have that add instruction here, so if I would just add this next time, well, I would go back to the beginning of the first row of my character, but not only I would be past the end, I would be past the end twice in a way, because I have rasterized 5 bytes here. So I would be 10 bytes too far, or 10 bytes after the first pixel of the row that I have already displayed. So I would have to go to the next line by adding 80 bytes, but then I would also have to go back by 10 bytes to be at the beginning of the next row where I need to display the next 5 bytes of my character. So going to the next line is 80 bytes, but minus 10, this gives 70. And 70 in decimal gives 46 in hexadecimal. And that's the reason why I have this add here. Every time I'm doing this, every time I'm looping through this block here, I will jump from one page to the next. So every time I go to the second page coming from the first one, I go back to the beginning of the row. But because it's the next page, well, it's effectively the next row. And every time I go back to the first page coming from the second page, I will get back to the start of the next row, because I will skip 70 bytes. So it's a little tricky, but if you want to simply try that out by writing a little program that spits out the addresses, that will make it very, very clear. So after displaying all the rows of a character, I get to this part where I'm adding something to DI. And so DI is the location at which I'm displaying the character in the video memory. Then I decrement BP and I loop. What can we do with this now? Well, the first thing is that maybe we can change the location on the screen where the characters are displayed. Here I have this value FC45. So I can display that value FC45, but that doesn't help that much, because starting with an F and knowing that we are working with 16-bit values, it is actually a negative number. Why is it negative? Well, because I'm just done displaying one character, so I need to go back up and then a little bit to the right to get to the next character. But so it's mostly going back, so this value is negative. And if I want to display that negative value, I will just have to extend the sign bit by doing FFFF and then FC45. And now I can see the value, and it's minus 955. So why minus 955? Well, the height of a character is 24 rows. So 24 times 80 bytes should give me the offset, except that since I have 2 pages, and here I'm in a way back to the first page with DI, because the number of rows is even. So DI is pointing to the first page again. I only have to go back up by 12 rows of pixels in that first page and not 24. And so 12 times 80 bytes is going to be 960 bytes. But we don't have 950 and 60, sorry, we have 955. Well, simply because now I would be, with my DI index, I would be at the beginning of the character if I would do that. And I don't want to be at the beginning of the character that I just displayed. I want to be at the beginning of the next character. And since each character takes 5 bytes for the width, then I need to go back by 960 plus 5, which gives me 955. Then maybe I can change this thing. And how could I change it? First, I need to know where this value is in memory. So if I look at the instruction add di, I can see that it's at memory location 2CFD, and it's a 4 bytes instruction again. Let's display those 4 bytes, px4, and well, fc45, here it is. So it's an offset of 2 bytes from the beginning of the instruction. And so the instruction is at current location plus 2, that's my offset, minus 100, because that's where I've loaded my com file. And so it is at 2BFF. Okay, let's copy this. Let's go to my little program here. And now I'm going to use my functions getWord and setWords. And let's call getWord with this address. Then to this offsets, what am I going to do? Well, let's say that I would like each character to be displayed a bit lower on the screen than the character before. Let's add 160. That's going to be 4 rows. And now I will write this value back. Let's run this. Back to DOSBox. Para2. And here we go. Okay. Well, is there something else that we could do with this? Well, what if we would change the name of the game? Changing the length is going to be a little bit trickier. Changing the characters is also going to be trickier because we have to work with the characters that we have here. The font, I'm not expecting it to contain anything but the letters strictly necessary to display that thing. So is there another word that we can make using the same letters and still keeping the length of 11 characters? Well, actually there is. But let's first figure out where that text is stored and how it is stored. Before displaying each letter, we've seen that we have these 3 instructions here. And so the first one is the offset to go from one line to the other. The last one is about setting the amount of repetitions for that loop. But the one here in the middle is the one that actually figures out what is the next letter that needs to be displayed. it loads SI, and SI says where the pixel data for the letter is. And so this SI value comes from DS, so that's our current segment, and then BP plus 1167. So remember, BP starts at 22, keeps on decrementing, and when it reaches 0, we exit the loop. Which means that BP is never going to be 0 here. It will start at 22, and then it will go through successive values by being decremented by 2 every time. So it will be 22, 20, 18, and so on. There is some sort of an array there that we are going to process from back to front. What is the address of that array? Well, it will be 0x110. This is the data segment, plus 0x1167. So it's 1277. Copy, seek. Let's have a look there. And now I'm going to display, well, 24 bytes, because it's an array of 11 elements, each element being 2 bytes, but it's as if the array is starting from index 1 and not from index 0, because index 0 is not going to be processed. So looking at 24 elements, I can see this. And starting from the back, I should have the indices for the addresses of the different letters. So that should be a P, that should be an A, that should be R, A. Well, I can already see that this is an A and this is an A and they have the same address. That makes sense. So para, T, or O, O. And I can also see that the letter O is there twice. P, E, R, and then an unused value here. And the P, E, R looks a lot like the P, A, R, only the letter in the middle is different. All right, so all this makes sense. So this is where we have the data that we need. Now, well, we can change it. So what is the address of this? I said 1277, and so we need to take 100 out of this. So I will copy this back into Visual Studio. So it's 1177. This is where I have the array that contains my title paratrooper. So let's write this here, paratrooper. Well, I'm going to loop over all these characters and display the addresses. So it's a loop that I'm going to enter 11 times. And in there, I will get the address of the letter, and that will be, well, get word. So I will take this address, and it will be plus, well, remember that the address is reversed, and also that I'm starting at 1 and not at 0. So it's going to be 11 minus I. So this goes from 11 to 1 times 2, because every element in the array is a word, and that should be the address. So let's do a console write line. Text I followed by letter X4. Okay, let's run the program. See if we got it right. And so we have this. So P is this 117F and 117F. The two O's are the same. The A, okay, R and R. All right, so that looks okay. So I've got all the letters. Now I'm going to build a little I don't need this line anymore. I'm going to build a little map. Let's make a dictionary from character to U short. So I will map the characters to their address in memory. So here I will say map of text I equals letter. Okay. So actually I don't need this anymore, and I can make that a bit more compact. Like so. And now I'm going to rewrite the text into something else. And I will say that new text is, well, that 11-letter word that uses the same letters that I found is a perpetrator. Alright, so let's rewrite this. I'm going to loop over these 11 characters again. A++. This time I do a set word, and the address is still the same as what I've computed here. So copy, paste. The value will be text of I. Sorry, new text of I, which I'm looking up in the map. Okay. All right, let's see if it worked. So DOS box, para2, and here we go. That sure looks like a less exciting game, but well, here we are. So that will be it for this second video. I hope you enjoyed it. Don't hesitate to let me know if I've got something wrong or if you have some precision to add. And yeah, see you next time.